Do that creamer as well.
Sorry for being late. I got sick over the weekend. So I don't know if I can speak for an hour and a half, 100 minutes.
It becomes a line that
Without stopping, let's see. There's a lot of tables here in front of the whiteboard. That one's been more speaking. See, maybe one of you or two of you can take that thing down or something. I don't know which way. You want it down or the side? Yeah, please. Is that okay for you? You're gonna be very tall. So a little bit of logistics this week. Actually, let's start with the big items. Exam is going to be Saturday, April 20th. I know there is at least one or two people who said they have difficulty that day with the exam. I'll work with them to make sure they get the same exam, just in a way that it works for them. The exam is, I think, at 10 a.m. So let's write that down. I think it's 10 a.m. And I also think it's in WBH, but I'm not sure the room. That would be a room with enough power plugs for everybody to plug in their laptops. Like I said, this is not the kind of theoretical exam, gotcha type of thing, you know? Like you have to study all these kinky little thingies because one of them is going to be asked, and what if you didn't study that one, right? It's going to be kind of like the homework problems with a little bit of setup that's suitable for like, I think the exam is like 5 or 6 hours long. I mean, maximum long. There'll be 2 problems, machine learning problems. You get your computer, you get the code, you get a data set. There's some basic task or requirement that needs to happen, like predict the digit or, you know, predict the class or something like that. And something that we have in mind that you have to do. Like if you run Bayesian regression, doesn't work immediately. You gotta do something. Maybe you have to regularize it, or maybe you have to normalize the data, or maybe you have to, you know, some work on it. I would expect the first people who finish, they will spend about 1 hour per problem. That would be the quickest, and most people will finish within 3 hours per problem. All right. Then this week, I'll certainly be at office hours on Thursday. Tomorrow, I have an appointment, but I can come back to office hours if somebody needs to see me. There's 3 people doing projects. If you need to see me tomorrow, no matter what, then I'll make it at office hours, but not at 6, probably around 6:30. We having a plan for Thursday after the math thingy? We don't know. Okay. All right. And we are a little bit behind with something for the homework, right? I'm sure anybody who wanted to have figured this out, but just in case. Just in case, in this homework, the homework, what is it, 6, right? You have to deal with features in a few ways. So you have some features for text, features for images, and then some feature processing, feature selection, so on and so forth. This is not so much machine learning algorithmic. It's just how do you prepare the data to fit into a machine learning algorithm, right? And that's kind of more of what information you have, what dictates how much you're gonna do independent of what algorithm you're gonna use. In some way you can think of how much information am I losing before I'm even doing machine learning. That's how you have to think of this process. A lot of effort today is put into this, many domains. I think we had this discussion already. So how about images? I don't think we talked seriously about images yet. And we're not gonna do it now either, because seriously would mean convolution neural networks. So if we were to do this for real with a convolution neural network, that would take the whole term. So for people who are really interested in images, you can take some, at least a month off for your schedule, and go back to your neural networks from homework 3 and say, okay, how do I implement a convolution neural network? In TensorFlow, there's already packages available. We can just run and see what happens. The reason you didn't have that exercise is because you can debug a neural network. So even if you run the network and it gives you a performance, it extracts the features, so on and so forth, you have no clue of what happened. You can try to implement it yourself. That will take a really long time. Instead, I'm going to show you something that's the same philosophy as the convolution neural network, but much more intuitive of what it's actually doing for features, for images. So if I don't do nothing, what would be my features for an image? The pixels, right? Okay. So if I take a picture right now on my phone, how many pixels I get? A few 10 million pixels, right? Each of them has 3 values, RGB, say. So I got right there like 30 million features, right? Just with one click. That's okay. I mean, if we have a high capacity machine learning algorithm, or I mean, information is there. You can argue, well, you have a big matrix, 3000 by 3000, and there's all these values in there, and you can take them as features. There's 2 questions. One, what kind of capacity, complexity a machine algorithm needs to have to look into 30 million values, right, per image? That's what we're talking about, number 1. Number 2, how much, remember these issues that we had with the spam-based data set and ADAPUS? How much a feature talks to the labels? Like if you look at the image and say, I want to determine if this is a tiger or not in this image, right? Binary classification, yes or no. How many of those 30 million values will be correlated directly with this issue, tiger or no tiger in the image?
Only the tiger is right.
Now, from a human mind, you can somehow, we don't exactly understand how we, the scientists, people can look at those 30 million values and figure out immediately if there's a tiger in the image, right? Even a 5-year-old can answer that question immediately. But no single pixel or subset of few pixels can answer that question, right? So this is a problem, this is a disconnect between how human mind works and how basic machine learning works. If you look at the basic machine learning algorithm, say the regression, what does it do? It adds different values to different coefficients, creates a score, but that's an addition, right? And that score, it's, if it's high, there's a tiger. If it's not high, there's no tiger. Human mind doesn't work like that, right? When you look at the image, you don't add up the pixel values with coefficients and end up with a score, and if the score is high, you say it's a tiger, right? It doesn't work like that. We believe now that human mind is much more close related to a neural network than with a regression or naive Bayes or decision tree algorithm, but that's up for debate. It's not really a neural network in the sense the neurons that fire in our brains they very similar with the non-linear actuator function, that's sigmoid, but there's no addition. In a neural network, every node has first a linear addition over the inputs, and then the non-linear function, right? Well, we don't have the linear addition, okay? So that we don't know how that works exactly. Anyway, I think I make my point very clear. It's going to be very hard to look on a pixel by pixel values and determine it's a tiger. Now, another thing for human mind is we don't look at an image by looking at 30 million values. Somehow, even if we blur the image or make it smaller or higher, or we you know have a less resolution image, we can still tell there's a tiger or no tiger in there. So we don't need a very crisp image for something like this. But algorithms, if we feed an image that's 9 million pixels, or 10 million pixels and 30 million values, they won't be able to do the synthesis of, okay, we don't need all those pixels to tell it's a tiger. That's why we need some new concept here, which in text we usually don't need it. In text is either word or sentence or bigram based features, which is what everybody's using, or direct feature extraction, you know, for domain specific, like in the spam data set. A lot of those features are people dream, like made up features, like somebody thought, what could possibly be spam? Oh, if I see the word free, I think that's a spam. So they invented the feature. Is the word free in this email? Yes or no? That's a feature. And then somebody else said, no, wait a minute. Spam might have to do with, I don't know, some sort of advertisement or link or something. And again, somebody wrote a little script. Is this feature present in there or not? Those are human created features based on domain expertise. I kind of have an understanding of what spam is. And based on what spam is, I query to see is this word or text or link or whatever text, right? I can do the same for an image. If I have a notion of what a tiger is, right, I could ask, are there enough yellow pixels? I don't know, how do tigers look like? Is there a contour that looks like with 4 legs? You know, so if I have a sense of exactly what I'm asking, I could try to heuristically determine what features I need. Okay. So, of course, I won't talk about tigers. I will talk about the digits that you have for the homework. This is something about the data. So, what we want to do here, it's similar in concept with what the CNN does, but far simpler. CNN does is going to look at an image and it's going to try to cut pieces of it and make features out of those pieces. CNN is going to look exhaustively at those chunks. So as I see here, A, B, C, D, that's a rectangle, right? I can cut from the picture. Ideally, I want to look at all these possible rectangles, which would be a lot of them, right? If I have in here 9 million pixels, how many rectangles can I get?
Tons.
How many
Way more than 9 million.
how many points do I need to determine this rectangle? 2. A and D, right? If I get A and D, I get a point. So I can pick any 2 pixels in the image, and that gives me a rectangle. So it's kind of 9 million choose 2 or something like that, right? That's a lot of rectangles to look at. The way this goes is like if I can look at all these chunks of the image and measure some metric on it. Say, for example, in these images would be the amount of black, because those are, you know, white and black images. So the only thing that matters is either luminosity or contrast or the amount of black pixels in there. The reason I need to look at a lot of rectangles is that unless you have domain knowledge, if you have domain knowledge, you could say, hey, you need to look at the rectangle that's in here. That's what doctors do when they look at people's, you know, scans and radiology scans and all that, right? they look at the picture, but they know the human body. They don't start looking for all the rectangles in there. They know exactly, okay, this is the, your liver, and I'm going to look directly at your liver. So they could cut the rectangle that matters immediately based on their domain expertise, right? Same thing in an accident. People take, there's like street cameras, right? Take pictures of whatever happens on the street. And if somebody like a police officer looks at the picture looking for something, a car that's been in a crash or a person that did something, they know where to look. They don't have to look for all possible rectangles in an image, right? But we're not that smart, so we don't know what rectangles matter for us. Now, you could in this homework, because those are digits, right? Try to figure out those rectangles if you like. It turns out we're not consistent in terms of writing digits. So if you look at all the fours that are in this data set, not all the fours look the same. So if you think, hey, if you look at this rectangle right here, you should see kind of a dark bar. That not all fours will have a bar, and not all bars will be in the same spot, and so on and so forth. So it's not a consistent thing. Somebody asked me this question last week or the week before. Can I detect subtitles in a movie? Can I read OCR subtitles in a movie? If that OCR is written by a computer, it's much more easy, because a computer will make all fours exactly the same, but a human will not. Many humans. So we want to look at rectangles like this, and we're going to have more than one. Those would be features for us. And we're going to have a metric for this rectangle. Things like how much amount of black or white or contrast is, or lines if we can detect lines. There's two sets of features that we need to look at. One is, say, amount of black in a rectangle, and the other one is if I have a rectangle, how much difference is between left and right or up and down in that metric. So my metric is the amount of black. For any rectangle, I can cut it this way and say, what's the difference of black between left and right? What's the difference in amount of black between up and down? That's essentially having two rectangles here and measuring the black here and taking the difference, and that becomes a feature. That's kind of like in ranking where I'm saying, it's not the amount of black that matters, because maybe I use a skinny pen and he uses a huge marker. He's going to have a lot more black in his image because his marker is big. But if you look at the difference in black, or the ratio in black between up and down, we might be consistent if we write this. If both me and him write down a 4, we may have the same proportion of black here versus here, even though I write with the skinny pen 0.3 and he writes with a huge marker. We want to create consistent features, right? Because otherwise the features won't be reliable for predicting, the targets. So we have two features, which is the metric over a rectangle, say the amount of black. I think the amount of black pixels is enough for the homework exercise. You don't need anything else. And then we have the difference left, right, up, down. The only problem is, how are we going to do this for all the rectangles? So now that we have a plan, which is not, this is the same idea convolution neural networks have, although they implemented much more sophisticated. They look at much more efficiently at many chunks, and they do comparisons between the chunks better. So this is the same idea, the convolution part is little chunks of the image. So to recap, our plan here is to cut a lot of parts of the image, and for each part, define a metric like the amount of black or the proportion of black. Measure that for the rectangle, and then also measure the difference left, right versus up, down. So for each rectangle, I'll have 3 features: the amount of black, the difference between left and right, the difference between up and down. So you can add or replace difference with ratios if you like. But for that, I still need a basic function that says, for a rectangle, how do I compute the amount of black pixels. For simplicity, let's assume all pixels are white or black, so I don't have to deal with grayscales. How can I do this efficiently? I have to use something, yes.
Calculate the area of black pixels and the area of white pixels. We can or basically subtract the total area minus the black area or white area.
Right, for a rectangle.
Yeah.
The problem is I have 9 million pixels that we said could be 9 million choose 2 rectangles. That's on the order of, I don't know, trillion, something like huge, right? So I can't just go, if I go naively for each rectangle, do something, that's not gonna work very well, right? So, everybody who asked me to waive the algorithm prerequisite for this class, well, this is where we need it a little bit.
How would you even store 9 million choose 2 features from each rectangle?
Right, we can't. Neural networks, convolutional neural networks, will have a way to not store them, but process enough of them to choose which ones matter. Of course, not all these rectangles matter, right? I mean, a lot of rectangles would be pure black, pure white. It won't be relevant for determining a form. But how do you know which ones are relevant, right? So nobody can store that many features. We're not going to be able to look at all of them and decide which ones we want. But the fancier algorithms might do a better job at selecting them, not storing them. And even if we store them, what algorithm can use them? Because it's still too many, right? So we need something called dynamic programming. Most of us heard of that, dynamic programming, which is, okay, we don't want to go over all the rectangles. We want to think of a rectangle here. It depends on what metric I have, but if the metric is the amount of black pixels, I can say, okay, what's the amount of black pixels in here? This is a random rectangle, A, B, C, D, right? I would write the amount of black pixels as a functions only of rectangles that start in the origin. So the key here is to say, I'm willing to, this is my image. I'm going to consider rectangles that start in here. So if I pinpoint this corner, how many rectangles I have now? 9 million, right? Not too bad. Now I want, assuming I can measure the black amount in these rectangles, that's only the rectangles that start in that corner, I want to compute the black amount in any rectangle whatsoever, not just those ones. So this is the idea here. If I can do the rectangles that start in here, what would be the black area here? How do I do that? It's easy, right? Because I can take the whole thing minus what? Minus OXBT, take this piece out. Minus OYCZ, take this piece out. But I have to put this piece back in because I took it out twice. Sounds familiar? Yeah. Okay, so it's easy to see how I can express that as a function of the same metric, black amount, in rectangles that all are pinpointing here, you know. So I need kind of the two-stage processing here. One stage is get the black amount in all rectangles that start in O, in the origin. That's 9 million of them. No problem storing 9 million real values, right, per rectangle. And then once I have that, I can immediately compute any black amount of any rectangle in this image. So part number 1 is this plan. It requires the metric to be decomposable that way. The amount of black pixel is decomposable that way, but not any single metric you can dream of can be written as a function like this. The second part is, how do I compute this? The black amount of all the rectangles that start in O. That's where dynamic programming comes into play. Because obviously I don't want to count the black pixels for every single rectangle. If I already know this, and I'm advancing. So how dynamic programming is gonna go? I already have this, and I already have this. This is the next pixel here, right? And I already have this. You have to write a dynamic programming function that says, okay, in what order do I need to compute these rectangles to use the previous values I have? Because otherwise I have to go again count the black pixels in there, right? So if I knew how many black pixels are here and how many black pixels are up to here, maybe I can compute how many black pixels are here now by just doing some very quick addition and subtraction in there. So just a quick question for the undergraduate students. You guys had algorithms, right? Good. This is a very, very easy dynamic programming, so it's not a problem. But you can see how, if you're naive about this, for each I equal 1 to 9 million, count the pixels. That can take a long time. Okay. So there's some more details here about how to do that dynamic programming. Okay. Needless to say, if you are not sure about dynamic programming, that's something that you absolutely need in a lot of places. So you need to recap that. I'm happy to do some discussion at office hours about it. That's it. That's the hard features. There's also a paper that talks about this, or 2 papers, a little bit more. And I think it's going to work quite well once you have those features. You can run, say, something like a boosting algorithm to classify the images. Now, hold on a second. We won't be, how many rectangles can we do? I mean, even if we store all these 9 million things internally, which you can very easily, with dynamic programming, you should be able to compute all these values. How many of these ABCDs chunks can you actually deal with? Here, right? So assuming I internally first compute all the rectangles that starts in O, then I need to cut out the features. I think the homework has some specifications, how many rectangles you need. 200? 100? Right. Are they picked at random?
Yeah.
Right. So I think by trial and error, because digits are so simple, we figure out 100 is enough. But I want to run an exercise. What do I actually need to do here? Like why it's 100 a good number? Go back to this. If I stick 100 random examples, maybe there's a picture with more rectangles in it. Yeah. If I stick 100 rectangles to this, right? I think I want to constrain them a little bit too. So maybe that's something I remember from last year or so when people were saying 100 is good enough, but you need to constrain the rectangles to not get these super skinny long rectangles or super, because those are not that useful, right? I won't need 100 features to make the differentiation, right, between, say, a 4 and a 7. There's some part of the image that probably, once I capture it, that I could tell it's a 4 versus a 7, right? So I would imagine if I see this line in here, if I somehow capture this part of the image here, a 7 won't have this, right? A 4 will have it. So same things between a 8, say, and a 1 or something like this. The good thing about those images is that they're all the same size, right? They're exactly the same size. So the question would be how this rectangle stuff works if my image is at various sizes. Because then I have inconsistent rectangles. The upper left corner of, say, 100 pixels by 200 pixels is not the same for every image. The bad stuff in these images is that they're written by hand, so there's no guarantee that the 8s are all written like an 8 and so on and so forth. So you can expect mistakes. 8 will be confused with 3s, right? depending on what rectangle it should be. Ones might be confused with sevens, 6, 5s, I don't know. The point is, we figured out if we stick 100 rectangles to this, which is for all separation of all digits, right? All of 10 classes. Pretty much every class will have some particular 1 or 2 or 3 such rectangles that will determine the image class. So if you don't succeed with 100, you can try 150 or 200. I don't think you need that many of these rectangles to create features enough to differentiate the images. This will be a different story if I have much larger images. These are 28 by 28, I believe. Suppose I have 3,000 by 3,000, things get complicated. And also if I have much more complicated images, things like, actual image taken outside in nature, trees and cars and buildings and people and so on and so forth. If somebody wants to try, it would be quite good for you guys to see, okay, if I use a data set with images, which I can provide, real images, how many rectangles do I need to do classification? Maybe not 100, you may need 2,000 rectangles in there. And the metric may not be the number of black pixels anymore in a rectangle, right? If I have a real image, I have to measure other things. We're skipping a part here that's called image segmentation. A lot of image processing, including machine learning, will require some segmentation of images, which is part of the graphics world. How do you look at an image and detect objects in it? And when detect objects, cutting the contour of whatever object is in the image, they of course mark where the contour is. So it's not just the contour, but where in the image that piece is. Having that segmentation of image into parts, into objects, will simplify the feature extraction a lot. So, but we're skipping that for now. I think you have a question. All right.
If you're doing segmentation with boosting, each of your stumps is corresponding to like a specific box, right? So then can you look at a point and say which boxes have a large margin and use that for segmentation?
So I take this box ABCD right here.
Sure.
Okay, that's a feature. Yeah. And
you use that feature in boosting algorithm. So those
Yeah.
boxes become associated with stumps.
yeah.
And you look at the margin
Yeah.
for a specific data point. Find the high margin stumps.
Yeah.
Look at those boxes. Does that do your segmentation?
Well, I'm not sure. So margins are meaning they help the separation a lot. I'm not sure the separation. So the fact that this tells me clearly that's for this ABCD. If I see just this, I say okay, that differentiates a 4 from a 9 or something. I'm following your question in the sense of, okay, can I have a very, very useful feature differentiating 4s versus 9s, but not necessarily cutting an object out? Because segmentation in image, in graphics, it's not picking up a discriminant. Segmentation is picking up the object out of the image. Right? So I have to think a little bit about that. My guess is that these are single object images, right? Every image in here will have exactly one object, which is 1 digit. So as far as segmentation goes, segmentation means cutting the object out, right? While I think you guys are gonna observe that critical features, say the one that boosting uses a lot, are not necessarily something that capture the whole thing.
So could you do a reunion of high feature?
Maybe. Yeah.
All right, are we all set with these images? So why use boosting then? Once I have the features, can I try something else? Boosting makes very few assumptions about data, right? Because it's an ensemble of trees, right? It doesn't need to say, okay, data's linear, it doesn't need to say data separables, it doesn't need to say, I need to figure out regularization parameters in advance, right? You need to tune them, nothing like this. Boosting works mostly for anything. It may take a long time to get there. I think you guys already know that, right? It may require some deeper trees, smaller trees, so on and so forth. But it's quite a robust algorithm in the sense it doesn't get stuck. It's not the most efficient, like regression might be more efficient if you would have the hyperparameters to start with in advance. But I think for images like this that you don't know what to expect out of this cutting, chopping digits off, boosting is a pretty safe algorithm. In fact, in my experience with the industry, mostly consulting, most people when they say, I've got a data set of some kind, images, tests, I know more about medical domain, so on and so forth. There's two kinds of outcomes of running machine learning before people ask data scientists to help. One outcome is I run an off-the-shelf linear program, it worked perfectly, right? So that I don't need to worry about nothing. The other one, it doesn't work. Somehow something is broken, it doesn't work. When things don't work, the first thing you should try is something like a decision tree with boosting or a naive-based algorithm. Because those algorithms have power, descriptive power, will tell you what happens, and they're quite robust into what they do. Trying a regression or a neural network, even if it works, it's kind of much more hidden in terms of why is it that it works or it doesn't work. That's all I have to say about those images. And let's see how you guys do. When is this homework due?
Either Friday or the 27th.
Friday, this Friday is what?
29.
Okay.
It
You guys
says
gonna-
Friday the 27th on the website.
Fine. I'm not worried about deadlines at all, other than you guys finishing the homeworks by the time TAs need to put the grades in, okay? So we'll put some deadlines on all the homeworks, whatever Kitchen and Ayush and Bagus, they can say, okay, this is the last time we're gonna take demos. And if you finish by then, that's great. I don't like penalties at all. I didn't like them as a student, and I don't like them as a teacher. If you get it done, it's fine. Okay, so are we ready to move on about these homeworks? I think there's some missing link on the data set. I found the data set. I don't know why the link is not working. All set with this PCA. Anybody did PCA homework? With the work? Good? Perfect. We need to move. Yes.
On this question, there's a link to sample code. The link doesn't work as well.
This one here?
Yeah.
In this.
On the assignment page. You list this like a Python starter code.
Number 6?
Yeah. At number 5, or problem 5, there's a link that says Python. Yep.
All right, I'll look at it. So those two things, data set and the Python link. Python link was probably provided TA who TA last time. I'll have to ask the TAs to look into them and see what they're familiar with. So now we need to move into, don't get scared yet. We need to move into some bigger topics. I'm gonna keep the projector on for a moment because I want to show you a picture, and so we're moving on to support vector machines. Those are dinosaurs now. But there was a time when people came to this class and all they want to do all term is to learn support vector machines because that was the thing 10 years ago. Now nobody, uses those. Everybody wants to do deep neural networks now. But I think there's a great amount of things that you can learn machine learning wise and mathematics wise from this. So we're not going to do this lecture as I did it 5 years ago when they were still the thing, but we're going to do today and at least Thursday, possibly also next Tuesday, discussing support vector machines. This becomes extremely mathematical, far more than what we've done so far. So everyone chooses their cutoff, where I'm going to drop off, the thing. That's fine. I'm going to state very clearly what's required in support vector machines, and then whoever wants to follow more math follows more math. Whoever doesn't, okay? There is few pieces here that we need. Some we already know. Some we need to add. One is margins. That's one piece. What else we need? We need a linear classifier or functions. The old our friend wx plus b, right? The integration function. This is a dot product right here, and this is a bias, three terms, so on. Constraint optimization. This clearly we've heard of this stuff and we've seen it. This one here, we kind of heard of it, but we never actually done it. It's the one that requires Lagrangian multipliers to be solved. And we saw it already once or twice, but we didn't explain how it works. So this is the Lagrangian. So that's kind of like, we've seen it, but we don't know it yet. And then we need duality. That's that part in here. It's new. We need how to transform a problem from what's called a primal problem into a dual problem. And we need kernels. Similarity. So we have a long list of things to go through, and what I would like to do is to start with some intuition today, and then worry about solving problems, leave that for next time. What I have here is a little bit of a picture. I'm going to skip this. Actually, let me start with this problem here. It's an example, right? Let's start here. High school. I have a function of two variables, right? X1 squared, right here. I'm not going to write it. X1, I could have done it on the board. X minus 1 squared plus y minus 2 squared, right? And I want a minimum of this function. Now, if I don't say anything else, so pretend I'm hiding this stuff, what's the minimum? These are real numbers, x and y. If I say, give me the minimum of this function,
1, 2.
when the minimum is 0, right? When x is 1 and y is 2. Easy, right? You could see that immediately due to the nature of being positive sum of squares. The sum of squares is at least 0 no matter what. But you could also have taken derivatives. If you didn't know the sum of squares is always positive, if you differentiate with respect to x, you get what?
X minus 1 equals 0.
2 times x minus 1, right? If that's 0, x has to be 1. And if differentiate with respect to y, 2 times 1 minus 2 has to be 0, so y has to be 2. Right. Now, the problem here is that there is a constraint. 2x plus y has to be 0. That's an easy constraint. In practice, it's less than 0 or more than 0, but it's not that different. Let's say exactly 0. Exactly 0 means 2x plus y equals 0 is this line right here. It says the solution has to be on this line. Or if it would be saying bigger than 0, it would be saying what? It has to be on that side of the line. Right? So now that I want to say, okay, find me the minimum of that function that satisfies this, I can't take the differentials like I did before, because they won't satisfy this, right? X equal 1 and y equal 2 don't have this property. So now what? That's kind of the same problem we had before, right? We had this constraint with alphas and PCA and so on before. We said we kind of want to solve them in the same way, but we need to account for this constraint. So Lagrange and many other mathematicians, about 1800, figured out how to do this, kind of make an analogous to the take derivative equals 0 for unconstrained problems, make it into a constrained optimization problem. So before I go into how that works, let's look at the intuition. This is the hard constraint. So the solution's gotta be on this line. This in here, it's the main objective. I want the minimum of that function, right? Or the maximum or something. And to achieve the minimum maximum, I need to draw these contour lines. That everything in here has the same objective value. So this line here, everywhere on this line, everywhere on this line, I get the same value for the function, right? What did we say? What's the minimum of this? X equal 1 and y equal 2. That's the red dot, right? The minimum here is 0, right? If I move away from this point around here, anywhere in here I get a 1. That's a 0. So I'm not looking at the constraint 2x plus y equals 0. I'm only looking at the objective. This is the minimum. And the more I go away, I get a 2, I get a 3. Farther I go, so the farther I go, the more this objective f is going to go. If I would be unconstrained, I would choose the center, which is the minimum. But I'm constrained. My constraint says in here, you have to be on this line, or on this side of this line. Which means I still intuitively want to get as close as possible to the center here. My purpose is to minimize the function, and the center is where the minimum is. But I can't go too far away exactly to the center because I'm constrained by this line right here. So the problem becomes, I want to get as close as possible to the center. That's what the minimum is. In terms of these contours, right? All those contours are equivalent. Anywhere in here, you get a 2. So as far as the minimization goes, it doesn't matter if you're here, 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 here. Anywhere in here, it's a 2. Anywhere in here, it's a 3. Right? So we want to get on a contour that's anywhere, like on a contour close to the center, but still touching the line, because we can't move away from this line. So where's this point gonna be? What's the contour that's as close as possible to the center, but still touches the line? Because any contour that is smaller than that will be invalid now, because any contour here will not touch the line anymore. So you can think about it this way. If my subject constraint there is this line, it's not this one because it has to pass through zero, but doesn't matter, any line. Any contour that crosses the line, it's valid. Because it crosses the line, it means I have valid solutions in there. Any contour that doesn't cross the line, it will be invalid, because it's not going to satisfy my constraint. So which contour will do both? Will be close to the center, but still touching the line.
An orthogonal projection?
What?
An orthogonal, like a perpendicular projection from the optimal point
To the line. Right. That is true if this is a circle.
Ooh.
Right? It's a circle in this case, but I can, if I modify that to be 2y minus 3 in here, that won't be a circle anymore. But he's right. The point is here. I was asking something less specific. How do you think of this contour that is the smallest possible close to the red point? That's what I want, to be close to the red point, right? But still has to touch the line, because if it goes away from the line, I'm invalid now. Hands up, who's with me? Sorry, I can't speak properly. Are we clear what we're gonna do? Let's forget about the math for a second, the arithmetics, and just follow the intuition here. If I start with a big contour, it's gonna be valid, right? It's gonna cross the line. The problem is that function is not gonna be minimal. Now what I do, okay, I shrink the contour, shrink. I like it because it gets me to the minimum. But eventually I'm to the point where I can't shrink anymore, because if I want smaller than that, I gotta move away from the line. So at what point do I need to stop?
There's just one point touching the line.
It's called what?
Tangent.
So this guy Lagrange figured out they always tangent. Always. The moment where you need to stop, they gotta be tangent. If they not intersecting, means you move too far away and now you're invalid. If they intersecting more than the tangent, say 2 or 3 points, then means you can keep going to the minimum. You still have way to go to the minimum, right? So what Lagrange figured out again is that if the best contour there cannot be neither passing like this, nor it can be like this. This is invalid. You move too close to the center. And this, you probably can find something better than this. That's the main idea of the Lagrangian multipliers, that when the moment where you get the solution for this minimum that satisfies the constraint, the surface of the constraint, 2x plus y equals 0, in this case the line, and the objective functions must be tangent to each other. Okay? That's the intuition. So how this goes?
Professor, is that also the same if it's not a circle?
Yeah. And if the subject is not a line. So here's what this guy Lagrange, is it here? I don't know. Show you that picture. It says, the moment when the magic happens, when the solution happens, these are the contours. These contours are not circles because the function is a different thing. This is a contour. Everywhere here get the same objective. Everywhere here the same objective, so on and so forth. And this is the constraint. It says that the contour you want for the solution is going to be the one tangent to the constraint surface. Now again, they don't have to be circles, because contours are whatever the function is, the minimization or maximization function. And this doesn't have to be a line, it's whatever the constraint is. Yes?
Can you just repeat what a contour means?
Contour means where the functions that I have has a constant value. Oh, this is the center, the function has 0. Everywhere in this space, it has a 1 value. So this is, I should say, f equal 1, f equal 0, f equal 2. Right? Because this is a circle. Everywhere on this circle, the value of the function will be the same. Everywhere here will be higher and higher. But sometimes you see this as a conic plot like that. I think my previous image on the left, that green one, was like a 3D plot.
If what the function was subject to was not a line, but was, let's say, also a circle or maybe an ellipse, then you could have the minimum be intersecting multiple points, not just one. I think if you had an ellipse around the circle, then you want.
You can have two solutions, that's what you mean.
Yeah.
I think that's possible, to have two solutions based on constraints, but usually it doesn't happen, but because usually you write two constraints. But I think it's totally possible to have, I have to think of cases like this. You're saying if I get a circle like this.
You had a circle and it was constrained by an ellipse.
Yeah, I can, but it's still a few number of solutions. You can't have like an entire.
If you had a circle constrained by a circle.
That's still a tangent, right?
But it would intersect everywhere if they had the same center. Then the minimum.
I don't think that's
what you should try.
Yeah. Okay, so how does this go? There's a bunch of math here, very easy to follow. What's the hard part is the tangent part. Because those two are tangent, the idea of Lagrange is to say tangent means the two tangents have the same angle, right? So the two tangents having the same angles means there is a ratio of differentials, meaning the two differentials go at the same angle, but there's a scalar that has to compensate for the ratio between them. So that's called Lagrangian multiplier, and this is the scalar right here. So what this is doing is saying, I'm going to take my function that I want to differentiate, and I'm going to take the constraint, and I'm going to say, there's got to be a ratio between their differentials that I'm going to try to find out. That comes from the fact that they have to be tangent in the moment of solution. So this parameter right here gets added to the constraint. That's a Lagrangian multiplier associated with this constraint. And this is the ratio between the two differentials in this point. Once I have this, the math is nothing, because it's the same exact math that you guys did for the unconstrained problem. It says, okay, you can differentiate with respect to x, right? What do you get? 2x minus 1 plus 2 alpha, right? And then you can differentiate with respect to y. What do you get? 2, 1 minus 2 plus alpha, right? Plus alpha here. And you still set the differentials to 0. But notice that there's this alpha in there. It's not like in the unconstrained case. And then I can also differentiate with respect to alpha, and I get 2x plus y. There's no surprise, that's a constraint, right? And it's going to be 0. If I would have 0 there, I would have 2x plus y would be constrained to be 100. I'll have 2x plus y minus 100 in here as a constraint. And now what do? Well, I can solve this. I can say what's x as a function of alpha, what's y as a function of alpha, and then I replace x and y into these equations here. I find the alpha is 8 by 5, here's x, here's y. Turns out this is exactly this point right here, where this alpha forces the two differentials in the solutions to be parallel, aka tangent, and then it just adjusts the ratio between them. Now, I know the math is very easy, and for this class, you only need to know this. Take the objective, add alpha times constraint, solve the differentials, get alpha, x, and y, we're done. But it'd be quite useful to know where is this coming from. Why this alpha gets added in there, and then it solves the problem. Again, this is high school level math. There's nothing magic about it if you understand the technique. But the conceptual of why I get to add a parameter per constraint and solve it this way, it's a little tricky. It has to do again with the fact that they're always tangent at the solution.
When we had multiple constraints as well,
Yes.
like over there,
Yes.
so that way will
Be alpha 1 times the first constraint
Alpha two
plus
times
alpha
alpha
2. Every constraint has a Lagrangian multiplier. And I have more differentials, da, 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 da. Quite a magic trick, right? Imagine if people have figured this out like 200 years ago. I think there's another example here somewhere. There's another one. Maximize x plus y subject to x squared plus y squared equal 1. I mean, those are very trivial stuff. I'm sure you can follow plenty of these simple examples. Okay. I think it's time to turn this off. So I'm gonna say we check this point with the understanding that we might get stuck a little later and we'll have to get back to it to see how that goes. Let's create some intuition for support vector machines. So first the geometry of it. So how do people arrive at certain algorithms? It's quite difficult to see. If I tell you the actual SVM algorithm, here's how you do machine learning, you have never guessed how people got there. Where's it coming from? So I'm going to go back to the margins. So I have this h of x. That's like regression. I'm going to call it in here though separating plane, hyperplane. So the drawing I have, this is the line. Obviously x is the data, b is some bias term, w is the coefficients. And what I have here is, here's a point. This is a minus point. This is a plus point. I'll say this is x2, this is x1. This is the plus side. That's the minus side. And this is the closest point to the plane. I don't know if you can tell I'm on some medicine that takes some explanatory power out of my normal. I think I do better than this usually. So here's my plane. Now regression, just to not confuse things, regression line or quantity is the other way, right? The regression creates high scores for plus values and low scores for minus values, right? So while a separating line geometrically looks like a line, don't confuse things, right? So this is Wx plus b equals 0. So any point on this line, geometrically speaking. So I want you guys to forget about regression for right now. Just think about geometry. Any point in this is the data space. These are the points, right? So there's other pluses here. And there's other minuses here. Maybe there's one right here, and one right here, and one right here. But I picked those 2 points which I'm cheating, of course, like always. Like I'm pitting them like opposite sides, nice, perpendicular. Those are the closest ones. I want to make a point. Any point on the line will satisfy Wx plus b equals 0 geometrically. Every point, but I'm assuming my data has no points inside here. This is the closest plus and this is the closest minus. So the margin is right here. Right? Didn't we say that? This is the margin. It's how close those points are to the line. No surprise that we're going to try to place our separating line equally between the closest plus and the closest minus. Right? We wouldn't want the line to be here or here. That's a discussion we had last week. Like we want this separating line to be in between them. So now, the first thing we need to do geometrically here is to figure out how W looks like. If W is a vector, how does W look in this space? So the vector of coefficients. It's one coefficient per dimension, of course. So how would it look?
Perpendicular to the line.
Perpendicular to the line. So if you look at W, suppose this is the origin right here. W is some vector that goes perpendicular to the line. Right? This is W vector. W vector. Okay. We know that from geometry. The normal, that's how it's called, W, we have the property that it looks perpendicular to the line that does the separation. Right? So, so now what I think everybody can realize is this is something in the board here. I'm going to ask you, what is this distance? That's a relative question to the point of view. If I'm here, it looks that big. If you go all the way to the back of the room, it looks very small, right? So we need to fix a camera point of view to not go up and down too much, like zooming, right? You can take any data set, multiply all the features by 1,000, it's gonna look a lot bigger, right? So we're gonna fix a fixed point of view so that this distance, it's kind of a reference point. But that, again, anything can be zoomed in and out up to that reference point, right? So we're gonna say this distance here is 1. Let's call this rho. This has to do with zooming for a reference, or if you want to call it normalization. It doesn't matter what the actual number is. We can multiply or divide with a constant to get it to 1. Or maybe call it scale better. So now because I picked these nice points, x1 is the positive point, x2 is a negative point, they all have this is the same distance, right? Rho. I'm going to do a little bit of math here. Wx1 let's talk about the zooming a little bit more. So what is it that we want to scale? What I want to scale is where this line here is, right? So I said this is the distance I want to scale. I was wrong. I want to scale where this buffer is. So I want to say here's Wx plus b. That's the positive side. And here I have Wx plus b. That's the negative side. I would like these to be the closest points to be at +1 and the negative closest points to be at -1. So let's make that clear. We want to scale. So this is the geometrical distance from a plane closest plus or minus, and then we scale closest plus, we call that x1. We want to have Wx1 plus b equal +1, and the closest minus, that's x2 right here, Wx2 plus b equal -1. Can I achieve this by zooming? So what do I have? Back in the beginning, I have a bunch of data points, right? Span base. I got a Wx plus b separating line between the plus and minus side. What do I mean by scale to say I would like Wx plus b to be, so the closest points might be a few minuses that are close to the line, a few pluses that are close here. I want to call these margins plus and -1. What do I mean by scale? What do I scale? I mean, I'm going to assume I can't change the data. Data x is whatever it is. So what do I scale? Rho is a debugging measurement. Rho is not part of the algorithm. I can multiply the W with a certain constant, right, to get this to be exactly +1 or -1. That's what scaling actually means. So it's the same like the point of view, depending where you look at it. Hands up who's with me. Okay, not too bad. Okay, so now I'm doing simple arithmetics in here. What happens if I subtract those two things? W times x1 minus x2 would be what?
2.
2. x1 minus x2. So this is x1, this is x2. So how much is the distance between x1, I say rho here, Isn't it that 2 row is the segment x1 minus x2?
Yeah.
Is you look at x1 and x2, those are 2 vectors. The difference between them is exactly this segment. That's row plus row, that's 2 row. Right? So 2 row is that. And now, I say this x1, x2 line is parallel with the W line. That's because I picked it like that. I picked x1 and x2 exactly opposing sides of plus and minus. I mean, you could say, what if there's no x1 and x2 opposing sides? This is a conceptual thing. I'm assuming I have enough data and I could pick the points that I like to, right? If they be full of 3 million images in here, I could pick the ones that are on opposing sides in a closer sense, right? So what does this mean? I'm gonna make a statement here and you tell me if it's right. The norm of W times x1, x minus x2 is the norm of W times x1 minus x2. Because they are parallel. They are in the same direction. It's easy to see that if they're parallel, one is the other times a scalar, and then immediately I can take the norm separately. If this is the same vector except by multiplied by 3 or 5, then this product is exactly that product. So then what? How does this happen? x1 minus 2, that's 2 row. Right? W is W. Where is this 2 coming from?
So these times that's minus 2 is 2, it's not right.
Right. This in here. So this in here is the 2. This in here remains here. This we said is 2 times the margin, and then 2 times 2 goes away. Rho must be 1. Yes.
I think the rows be different.
Hmm?
They're not. Like say like x1 and x2 are spaced in different places. Like,
Right. So this is a conceptual explanation. It's not related to span base or digits data synthesizer. I'm assuming I have enough points in this space, enough density of images or emails or patients, that I can pick within the closest minuses and the closest pluses, I can pick opposed sides plus and minus, such that this line is perpendicular to the line. About being exactly halfway through, we discussed this before. Any a square loss or whatever optimizer would put the separating line not here or here or here, but rather in here, right?
okay.
So actually that's going to be obvious in a different way. If I want to maximize this margin, if I tell you from here to here you have a certain amount, but you want to maximize the minimum out of them, obviously you're going to put it in the middle, right? Because anyway you put it on this side, this becomes bigger, but that's smaller. So in order to, if I say I want to maximize the distance to the closest point, you definitely want to put it in the middle, right? So let's see how many of those things are clear so far. What do we have? We have a separating plane between plus and minuses. We looked at the closest minuses, closest pluses. And we said we want to really address this distance between how close are the points to the plane. This concept we've seen twice. We've seen it in the margins derivation last time, but we've seen it before with active learning. Active learning is related to this margin. The reason the points close to the plane play an important role is that those are the points that kind of not allow you to have large margins because they are close to the plane. If all points will be far away, the margin will be far, big. So now we look at this purely geometrical. We say, if this is my plane, Wx plus b, let's fix a scale so that the margins equally distant row plus side, row minus side, have the closest points at Wx plus b equal plus 1. And of course, here will be what? Wx plus b equal plus 2. And here will be plus 3, right? It's like the contour thing. And the same thing in here. If this margin goes at minus 1, anything here will have Wx plus b equal minus 2, right? But the farther I go from the line, the less interesting it becomes, right? I mean, who cares about what happened there? Those points are the ones that are so obviously positive examples that I don't need to focus too much on them, right? That's what is related to active learning. And active learning is the points that are close to the line that dictates what needs to happen. So once I've done this, I've done some simple calculation, 3 steps. One is saying simple division, that's a 2, a subtraction here. In here I say, okay, the margin is actually the difference between the closest points by half. And then I use the fact that these are parallel lines to get that the margin is 1 over W. Now, if I wouldn't have a scale fixed, remember I fixed the scale, I said this have to be 1, I could easily maximize this margin, right? How?
Multiply W by a million.
Divide. Right. It's 1 over W. So I could make this number very big, right? If you want a big margin, all you have to do is make W's very small, right? But I can't do that because I already fixed the scale. Right? I fixed the multiplying W with some constant. We already said it's effectively deciding what number is this. Is it plus 1? Is it plus 3? Is it plus 7? Is it plus 0.01? So we already fixed the camera point, the scale. We can't just multiply W by a constant now because that's already a done deal. Is that too mathematical? That's why we need to fix the reference point, because otherwise, which is the, we need a constraint here. I think that's obvious, right? Otherwise, it's just a matter of zooming the camera in and out, and we change the margin. We don't want the margin to be depending on where you look at it from. Like I said, if I look in here, it looks really big. From the back of the room, it may look really small. That's not, I don't want my definition of margin to depending on who's looking at it or from how far away. So I want to fix a scaling point where this is a 1, and therefore I get this relationship. So now what do we want? To maximize the margin, that is minimize this. Right? Because obviously maximizing this means minimizing that. But we need to have that constraint, the scaling that we imposed, we need to put it as constraint here, because otherwise, again, multiply that or divide by a million, we get the large margin. So subject to the scale constraint. So we want two things. I want to maximize the margin. I'm going to say here to be more clear, that's the stroke. That's the same as minimizing W, obviously. But what's the constraint that we imposed? How do we define the scale? Wx plus b is +1 for positive points, right? So Wx plus b is +1 for y equal +1, right? The label. And Wx plus b equal -1 for y equal -1, right? For the linear group. But we didn't actually say everybody has to be +1. What did we actually say? The closest points have to be at +1, right? We defined this margin for the closest point, not for other classes. Obviously would be at +2, +3, so on and so forth. So this equal sign is not correct here. We say we want all the positive points to be at least +1. And all the negative points at most -1, right? Remember when I could do this with only one equation because I get y to be combined, and I can replace this whole thing with what? Y times Wx plus b, because I multiply the y, and then I need to get greater than 1. This is for all data points. Right? What this is saying is those two things. Because if you multiply this one with +1, it stays the way it is. But this one with -1 just changes the sign, becomes +1. It says, I want all the points to be at least at +1 if they're positive, and at most at -1 if they're negative. That means it ensures the margin there. And this is saying, I want to minimize this. So now I have a familiar Lagrangian problem, right? That's what I have. I have an objective, and I have a bunch of constraints. How many constraints do I have? Yeah, it's written as 1, but it's for every single data point, right? So how many constraints do I have?
Number
N. This is N constraints, right? So if I have 1,000,000 images, I have 1,000,000 constraints. We got to be very careful with these problems because sometimes there are not that many features. So how many components the vector W has? D, right? D in span base. D is how much? 54, and N is 4. If I apply this to span base, I'm going to end up with minimizing a problem of 54 parameters right there, subject to 4,000 constraints, right? One constraint per data point. Two things in here. Let's not get scared yet. The whole magic of support vector machines is to eliminate irrelevant constraints. So the name support comes from the fact that in this algorithm, we're not going to use all 4,000 N constraints. Part of the algorithm is determine this is a constraint that matters, this is a constraint that matters, this matter, right? Remember, there's one constraint per data point, and it's going to say this point here doesn't matter, this point here doesn't matter, so on and so forth. It's going to identify what's called the support vectors or support points. And even if I have 4,000 constraints, only 57 or 77 of them will actually act as constraints. The other ones will be loose. Loose constraints in optimizations are the ones that whether you put them in or not, they don't change the solution at all. Active constraints are the ones that when you put them in, they change the solution. When you don't put them in, you have a different solution, right? Obviously, the problem I show you on the board, that was an active constraint, because without that constraint, you would have got a different minimum. There's another thing here. We don't like this mathematically. This, not nice math. So we need this to be the norm that's easily differentiable, you know. So we're gonna say minimize 1/2 of the square norm. We wanna, it's very, in principle means the same thing. There's a discussion between L1 and L2 regularization here. That's the same discussion. We want to do the one that allows us to do the easy math. Okay? So now, where I am, I have this well-defined mathematical problem. Give me 54 coefficients that minimize this, subject to these constraints. And I want an intelligent algorithm that will determine quickly what constraints don't matter. I can tell you from constraint optimization that if you have 4,000 constraints with 54 parameters, two things are gonna happen. First of all, there's no solution. There's too many constraints to have a solution. It's impossible. And second of all, most constraints you can throw out, they already gonna be satisfied by stronger constraints. Constraints are often hierarchical. You keep the stronger one, like x1 squared, something has to be smaller than 1. There's another one that says x1 squared has to be smaller than 3. Yeah, but if it's smaller than 1, it's going to also be smaller than 3. So how do I throw out the constraints that are loose or easy to satisfy or already satisfied before because of the other constraints? And two, how do I deal with the fact that this cannot have a solution? There are too many constraints. You have a question?
Is that the same as L2 normalization? What you did there? Half of normalization of double square.
This is the same form mathematically, but in here this is the objective. Okay? This is our objective here. In regression, our objective is to minimize the square loss, right? This in here is the declared objective. We want to minimize this quantity, subject to the scale that we impose, which says all points have to be here. So we need to find a way to do a solution here. The solution is going to have to be, say, okay, you got to allow some errors. You got to allow the possibility that at some point will be in here. We don't want it, but it's going to happen. And secondly, we're going to identify, we need to identify what constraints matter. To do so, we have to take a bunch of derivatives and determine which constraints are active, inactive. In fact, we're going to measure something like a constraint force. It's a parameter, force. If that's 0, means the constraint is useless. We can throw it out. The stronger that force is, the more active the constraint is. And obviously a point here will have a strong force to the plane, will influence the plane. A point far away will not. All right, so that's what's going to happen next time. There'll be a homework on support vector machines. Yes?
Will the number of like support vectors always be less than or equal to the number of like features? Like, because I think what you're saying is that the system's overdetermined. If you have 4,000 constraints or 4,000 constraints subject to like whatever amount of room.
I don't think it's a deterministic view like this. I didn't mean it in a linear algebraic sense. I mean it if you have 54 parameters and you have 4,000 constraints, you can't possibly hope for a solution.
But it's not like the overdetermined, underdetermined thing in a matrix.
The support vectors are a lot smaller than the size of the data. But the more support vectors, you have more features.
If I could, I have something.
Because
Who asked the question?
It's more features. The space is more features.
Yeah.
The height is more features for dimensions. Allows more.
No, I was just thinking like in a purely